Hey guys, and welcome back. So this week we have been talking about the electron. So this unit has been all about the atom. The first half of the unit we talked about nuclear chemistry, so the protons and the neutrons and the nucleus. And now we have moved on to talking about that negatively charged electron that exists in the electron cloud around the nucleus. Now today's lesson is probably the trickiest thing we've done so far in this class. So please make sure that you are paying attention. We'll do some examples, and then if you're having trouble, definitely set up a meeting with me on my bookings link or come to my office hours from 10 to 11 because I definitely don't want there to be any confusion about what we're about to go over. All right, so let's go ahead and get started. Today we are talking about something called electron configuration. So on the left-hand side here, we have our Bohr model. So you guys did Bohr models a couple of days ago, and we know that electrons orbit the nucleus. You guys went through and did that practice problems on the slideshow where you filled in the electrons in each of the energy shell. We know the first energy shell gets 2, then the second and third get 8, and so on and so forth. That is a very basic model of the atom and where the electrons fall in those energy orbits. Like with most things in real life, the truth of it is a little bit more complicated. And when we talk about the structure of the atom and where these electrons are, a better way to display that is with the quantum mechanical model. So this is where the electrons orbit in a 3D manner that's a little bit more complex. Really, what we're talking about today with the orbitals and the shapes of their orbitals is in relation to the quantum mechanical model. So we're just going to learn a little bit more in depth that these electrons are not necessarily located just in these simplistic rings. Okay, so all you need to know is that the difference between the Bohr and the quantum mechanical model is that the Bohr model is just more simplistic in the display of where the electrons are in those energy rings. So we've already talked about the energy levels in the Bohr model. Okay, we know that electrons exist in the energy levels in the rings that are around the nucleus. But each of those energy levels also have sublevels that electrons can fill. So the first energy level has one sublevel, and that sublevel is 1s. Okay, so then we just refer to that sublevel as 1s. The second energy level has two sublevels, so 2s and 2p. And this will become a little bit clearer when we take a look at our periodic table here in just a few minutes. And then the third energy level has three sublevels, so 3s, 3p, and 3d. And then there's also F levels as well. But for us, what we're getting into, a lot of times we don't necessarily dive into those categories, but I will show you how to do electron configuration for the higher elements as well. So for each sublevel, there are a maximum amount of electrons that can be held. Okay, so in the S sublevel, it gets a maximum of 2 electrons. In the P sublevel, it gets a maximum of 6 electrons. The D sublevel gets 10, and the F sublevel gets 14, okay? So in any one of these given sublevels of these energy rings, there's a maximum amount of electrons that each can hold. So just a reminder, the Bohr model is simple. It's got distinct energy levels, and we look at it as those electrons moving in circular motion. The real-life atom follows more so of this quantum mechanical model, which is complex. It has multi-level energy levels, and there's 3D movement around the nucleus, right? We know that these electrons are not just spinning in circles. They are moving in a 3D pattern because we live in a 3D world. So if it's not a circle, then what do these orbits look like? So again, there are those 4 types of orbital shapes that go along with S, P, D, and F. And just a little mnemonic to help us remember that is some people do forget. So some people do forget S, P, D, and F. And these are the shapes of these orbitals. So instead of moving in those circular 2D patterns, if an electron is in these corresponding orbitals, then their pattern is going to follow the shape of these orbitals. So the s orbital is a sphere, so not a plane circle, but a sphere. The p orbital, we have these two oval-like shapes. It's almost like an infinity symbol. The d orbital is a clover, and then the f orbital is this multi-dimensional kind of double clover shape. So if you were to find an electron in, let's say, the d orbital, it's not just going in this basic circle. It can be found anywhere along this shape. Okay, so these are the shapes of our 4 orbitals. And remember, each of these orbitals has a maximum number of electrons that it can hold. So now here is where the periodic table comes in. Okay, so if we were in class together, we would be coloring a periodic table. Since you guys are virtual, I'm going to give you a periodic table that you can pull up and reference with these blocks on it. But these are the blocks that tell us what elements will have electrons in what orbital. So our S block is going to be on our left-hand side. So our S block is our alkali metals and our alkaline earth metals, and helium as well. So helium is a part of the S block. So when we go to do the configuration, he'll be in the S block. The P block are going to be on the right-hand side, right? So starting here in our typical A groups for our family, right? So 3A, 4A, 5, 6, 7, and 8. So our P block is right here. Our D block are the transition metals, and then our F block are the rare earth metals. Okay, so S, P, D, and F. Now what this means is that, kind of like with your metals, nonmetals, and metalloids, if you identify an element, so let's say oxygen, I would ask you, what block would oxygen be in? Oxygen is over here with our nonmetals, so you would know, well, oxygen's in the P block, so it's definitely going to have a P sublevel. Okay, so it just helps you identify where these sublevels are and what sublevels these elements have. Okay, and then this is just a image and a depiction of what an atom looks like as a 3D model. So this would be an image of the quantum mechanical model. Okay, so what is the meaning of this? What is the application of this? Because this is a lot of information about 3D orbitals and where these electrons in the electron cloud are moving. Well, the application for you, so what you have to be able to do is determine the electron configuration for each element. Okay, so I should be able to give you an element and you can give me the electron configuration, which is what we're going to do now. So basically, electron configuration is a code. It's just a code for an element. It's a different way to write the element to code it. And all codes have to be written and broken, and the same goes for science. So one of the codes is called the Abafu principle, and this code uses a series of letters and numbers to write a code for the amount of electrons in an atom. So basically, this code is just telling us how many electrons are in an atom, okay? And because we're still talking about neutral atoms, remember your electrons in your atom are going to be equivalent to your protons as well. So your atomic number. So when we write electron configuration, the arrangement of the elements is based on the electrons and their orbital energy. So what is their energy level, 1 through 7? The shape, so S, P, D, F, and this is all lowercase. And then the spin, whether it's clockwise or counterclockwise. When electrons fill orbitals, they have to be in opposite directions. So if you have 2 electrons in the same orbital, one will be spinning in a clockwise direction and one will be spinning in a counterclockwise direction. So before we go through the process of how to write the electron configuration, remember, each block has a maximum number of electrons associated with it. So S, P, D, and F. Remember, the S gets 2 electrons, and that's because there are only 2 elements on each row. Okay? P gets 6, because there are 6 elements on each row of the P block. D gets 10, again, 10 elements on each row of D block. and then F gets 14, and again 14 elements on each row. So if you think about the rare earth metals, there are 14 elements in each row, so that's a maximum of 14, because remember our periodic table is arranged in order of increasing atomic number, therefore increasing electrons. So the rows are associated with how many electrons can fill into each element. Okay, so these numbers are going to be definitely important for us. Here is a periodic table that you're going to have access to, so I will post it for you that you can pull it up. We have to remember the numbering and the blocks for each of these. So remember, the blue is S block, the green is P, the orange is D, and then the purple is F, okay? Then the numbering, so here you see with hydrogen is 1, 2, 3, 4. The numbering is based on just the period that it's in, except for the D block, okay? You see the D block here is, it's 3 even though it's in period 4. That's just something you have to remember, okay? So just remember that for the transitions, when we get to D, D block starts with 3. It does not start with 4, even though it is in period 4. And that's just something that we have to commit to memory, okay? So how do we do this? Here are the steps. Number 1, you have to identify the energy level and the sublevel of your element. Okay, so the example here we're doing is carbon. So to identify the energy level and the sublevel, you need to first identify what period it's in. So what period is the element in? And then what block is it in? So if we take a look at carbon, and I'm going to just switch back to this periodic table right here. Carbon is right here, okay? So carbon is in period 2, and it's in the P block, all right? So carbon is going to be 2P. Now it'll be 2P something, but we'll get there in just a second. So the period is 2, and the block is P, because it's in P block, and it is in period 2. Next, we have to identify the place that it appears in that block. So is it first, second, third, etc.? Well, let's go back. So carbon is in 2P. So this is what we're looking at because we're only looking at the P block right now. And carbon is the first, second element, okay? So carbon is the second element in the second row of P block. So the denotation for carbon is going to be 2P2, okay? So 2P2. 2 for the energy level because we're in period 2. P because we're in the P block. And 2 because carbon is the second element in this row. So boron is first, carbon is second. So it's 2P2. Then you put it all together. So 2P2 is going to be the final code in electron configuration. Now we're not done, because even though that configuration is for carbon, when you're writing electron configuration, you have to write the configurations for every single element before it, okay? So for every element you have to write a configuration for, you would need to include it before your final element, okay? So we know that the configuration is going to end with 2P2, but we have to start at hydrogen. So let's go back and take a look. So hydrogen, this is where we start for every element. And then the element you want the configuration for is where you're going to end. So we start with hydrogen and we end with carbon. Well, if we start over here and make our way through, hydrogen is 1s1 because it's in the first period. It's in the S block and it's the first element. Helium is 1s2, okay, because it's in period 1, S block, second element. Now, because we have to continue with helium, our first code is going to be 1s2, okay, because we go through the first period. So 1s2. Then we will drop back down to the S block, okay, and it will be 2s1, 2s2, because beryllium is 2s2, because it's in the second period, in the S block, second. Now, because we're going through that, again, our second code will be 2s2. So it's 1s2, 2s2. Now there's no D here because the transitions are